Good evening. Today I'll be showing how to make a fluent 2D flow simulation of combined Poiseuille and Coet flow. And let's get right on into it. We're going to be using ANSYS Fluent. So we're at our workbench. We're just going to start off by creating a project. And first we're going to make a geometry. I like to use space claims. Let's go ahead and use space claim. Let that load up. Okay, so it looks like we're in space claim. We can go ahead and pick a plane. Like pick my X and Y plane. Okay. So since we're doing 2D Poiseuille and Coet flow, and it tells us that the conditions are going to be viscous, steady, laminar, and compressible. Free stream is at 5 meters per second. The top plate is moving at 3 meters per second, and the bottom is moving at -2. The length and height, they want it to be 150 times the height. So let's go ahead and just make a rectangle like this, and then 150 times. So I'm going to make this 150 millimeters. Then go ahead. This one. Okay. As you can see, 150 and 1 millimeter. That looks good. Sketch. And here we have a very long 2D rectangle. Let's edit the mesh. Add a second to load up. Perfect. Looks like we're in a mesh mode. Go ahead. Selecting our bodies, I suppose. We can start by selecting the edge. Make this top part. Press N. We're going to call this the top. It's going to be our top wall. Down here, we're going to name that bottom. Bottom. Then we're going to, the entrance, inlet. And then lastly, outlet. And that outlet. Very nice. Okay. Perfect. So we have our names. Now we're gonna have to go ahead and create a mesh. We're gonna insert. We're going to go to sizing. Hang on 1 second. Yes, sizing. I'm going to click top, top. Okay, so the two edges I had were the first ones were the top and bottom. I split them up at 150. The second were the sides, and then the last was the face mesh, and then there you go. You can see your full mesh. Um, we already updated this, so now we can go ahead and small screen this and go back to our workbench and go here to update. And then we're gonna want to go to setup, and then to go to processors we use for double up. It's like we're in. Okay, so we're finally in. Let's go ahead and start with this looks okay. Materials is going to be fluid, air, and we are going to do air. Okay, and this constant is going to be fine because when we solve for our Reynolds number, we don't want to be above 2500. That way we can know that we're in complete laminar flow. And so by doing that, we're going to multiply by the values that we're given, are 5 meters per second times our length times our density divided by our static or dynamic viscosity, which is shown, and that's going to be under 2500. So we can go ahead and leave that like that. And we can go ahead and grab our boundary conditions, inlet. Inlet looks correct. Let's go ahead and edit the values for that. So, normal boundary, that's okay. Our velocity magnitude is going to be 5 meters per second. Nice. We just the boundary. That's fine. Yeah. So meters per second. Apply. Matter of fact, we can just do direction. That way we know we're doing it right. Apply. Close. Now we can go to our. Let's make sure that this is the correct one. Oh, oops. My outlet. I did not mean to press internal. So my outlet, nothing's gonna change there. So, okay. This looks fine. Then our walls, our top wall. And the speed is going to be 3 meters per second. The top wall direction is going to be positive. Standard apply. And then the bottom wall as well, but it's moving in the negative direction at 2 meters per second. In the slip condition, moving wall, apply, close. Let's double check the top wall. Close. So our walls are done. Our outlet and inlet is also done. Now we can go ahead and move on to our second 150. Okay. Okay. So I believe that we can go ahead and move to our run calculation. Operations. That should work. Should be fine with what we have. There's nothing else that we have to double check. So let's go ahead and calculate. Okay. Looks like our results are already here. We can go ahead and we're going to start with our graphics. Let's do contours. Double click that. We're going to want to do velocity contours. Velocity magnitude, and inlet, interior, and outlet. And we can go ahead and display. So here's our first contour. See how our boundary layer develops. It's quite nice. Very slow velocity, no slip condition, and high velocity at the top. As well as the top one, you can see how since it's moving in a positive direction, the velocity is going to not get as mitigated as it is on the bottom that's moving in the negative direction, right? So the first question tells us to show the velocity contours with vectors. Vectors show, okay. So to do that, we're gonna have to have our velocity. Then we can go to vectors, double click on that. We want our velocity vector, yes. That's fine. Magnitude. Same thing here. And we can do our vector options, I believe. Color, we can make it, let's make it white. So it can be seen. We can apply that, close that, save this display. And you can see here the development of our little vectors. Very nice. And then we can go ahead and we can add two. Close, click, add two. There you go. And then you can see our velocity magnitude as the, vectors and the boundary layers. So that's quite interesting. Look at that. Each vector. Pretty neat as you see the contours. Next, it asks for the pressure contour, so that's not going to be too bad. Go ahead. It's a new one. Pressure. I'm going to do total pressure. Close. And then as you can see, total pressure changes from the beginning all the way to the end because of the increase, because of the initial velocity. It will decrease as it gets towards the end, so you won't have that much of a. There's going to be a negative pressure gradient pushing through here. So there's going to be less pressure here, more pressure here due to that static plus dynamic, where the dynamics are and dynamics less here, but the static stays the same. Next shows asks us to show the velocity profiles at the mid and end section on the same graph. So we can go ahead here to our plot. Okay. What the question asks us is to show the velocity profiles at the mid and end section of the pipe on the same graph. So here at the midline, I made it at 0.075 because half of the length of the x is going to be at 0.075, and then the end line is going to be at 0.15. But then our y values are always going to be from 0 to 0.01. And then since it's asking us to plot directly our profiles, I can go ahead and zoom this in like this. And I mean, nonetheless, right? You can see that the profiles are essentially the same. They're about the same, so that's what's important there, because that's the velocity profiles at the mid and end section of the pipe. They're going to be almost identical. If I can see how to zoom in. They're basically identical, and so that's going to be that. And then our last one is going to be determine the maximum velocity and height at which the velocity occurs. Well, this is our y-axis, right? And so we know that it's around 0.006, but it wants us using fluent results, so we'll go to results, and we will go back out to this actually. Updated, we can graph that. I'll load up.